énormément.
All right, so I hope everyone is back from the break. I think we should start with the next talk, and Dorsaf Cherif will give us a presentation on the topic of no arbitrage condition from discrete time to continuous time. So the stage is yours.
So hello everyone. Can you see my screen?
Yes.
Yes.
Okay. So, okay.
Perfect.
Okay. So first I introduce myself. I am Dorsaf Cherif from University Tunis Al Manar. I want to thank the organizing committee who allowed me to participate to this conference. Today I will expose some results from my work directed by Professor Emmanuel Lepinet from Paris Dauphine. So in this talk, I will introduce first the probability model of a financial market. Then we define what we will call elementary portfolio processes. Before introducing the weakest possible non-arbitrage condition called AIP, we aim to construct the set of continuous time portfolio processes. To do so, we will propose new topologies on L0 using the conditional supremum. And finally, we will extend the AIP condition to the continuous time. So this is the plan of. So let us first introduce the probability model of a financial market. So we consider a market with de-risky assets, for example, contracts on petrol, on corn, on whatever, with prices at time t given by a vector st in the positive cone of Rd. That is, at time t, the price of the first asset is st1, of the second asset, etc. So this represents the prices, and the quantity held by an agent at time t will be denoted by theta t, called strategies. As prices and strategies depend on the market informations, like for example, political situations or health crisis or the weather, etc., we need a set for all these states of the market, and then prices and strategies will be functions depending on this information. So it is very convenient to modelize with the probability framework in the following way. So the model is given by a complete filtered probability space, omega ft p, where t is the time horizon. Omega will be the space of all possible states of the financial market. Sigma algebras ft, sigma algebra ft will represent the information of the market available at time t. And then we will consider ft adapted RD valued non-negative process for prices and ft adapted process for strategies. We precise that strategies are allowed to be non-negative, to be non-positive, sorry, which corresponds to a debt. So this model is when the time t is in the real interval 0 big T. So that we call continuous time, i.e. the trading is instantaneous. Our objective is to generalize some notions from discrete time to this real-time model. Let us first speak about the discrete time model. So in discrete time, the agent invests a discrete finite number of times. For example, every day weekly, monthly, whatever. So we consider a discrete time for filtration. So T will take values 1, 2, 3, etc. Now we want to obtain the amount of money held by the agent at time t when he invests quantity theta t at a set whose price is st. So this is what we call the portfolio value at time t. It's given by the scalar product st theta t. Then under a famous condition called self-financed portfolios, which is this condition, a T-terminal discrete time portfolio starting from with zero initial capital at time t will be the sum from small t to big T of theta e minus 1 delta st. So here the trading begins at time small t and end up at time big T with this this formula, and these are the instant of investment, the times at which the agent trades. Now we go on a very famous condition in the study of the financial market called non-arbitrage, introduced in the 70s with the model of Black-Scholes. So what is the arbitrage? The arbitrage is the possibility to earn money beginning from zero capital. So we begin with no capital and we end up earn money. Otherwise, we say that there is no arbitrage. So if this is not possible, we say that there is no arbitrage or no free lunch. The most important theorem will be is the following. So the NA condition is equivalent to the existence of a equivalent probability measure such that the process of prices is a martingale for this new measure. For a nice exposition of this, one can see the book of Kabanov cited below. Now, we aim to work in continuous time, that is to trade in high frequency. Indeed, in the financial market, now we speak a lot about high frequency trading because it's done by computer. So from discrete time model to continuous time, the instant at which the agent reorganizes his portfolio will be closer and closer. Before proposing our way of doing things, I will give some motivations and some historic. One can ask if we are the first ones who constructed continuous time portfolios. The answer is no. The classical definition of continuous time portfolios is by the stochastic integrals. It's in L2, but ours will be in L0. Furthermore, to extend the NA condition, we need a semi-martingale process for prices. So a second motivation to our works was to have a model when we don't need this condition. Also here, we are not the first one. Processes which are not semi-martingale are appearing more regularly in the literature. For example, one can see the article, No Arbitrage Without Semi-Martingales of Jarrow, Potter, and Said, who attempted to find a general class of prices which need not to be semi-martingales that do not permit arbitrage. Their approach was to require a fixed time between successive trades. The fixed time can be as small as one likes, but once chosen, it cannot be changed. So these are some historics in the same topic. Now let us turn to our approach. Our first step for continuous time was what we will call elementary portfolios. And as a second step, we will consider their limits in some way. In elementary portfolios, the agent no longer trades at a finite number of times fixed in the beginning. But as a first example, we can say that the agent trades at arbitrary deterministic times. It's a finite number of time, but the number of time is not fixed at the beginning and nor the instance. So uh, uh, a portfolio value will be sum beginning at time small t and the time horizon is big T, will be the sum of theta t minus 1 delta STE and T1, T2, Tn will be the arbitrary deterministic times of trading. A second example of elementary portfolios will be when the the instant of investment or of trading are at some stopping times. In other words, the trading is done when some market conditions are satisfied. So the portfolio value will be it's the same formula, but the index times are stopping times. I can see that the second example is really close to reality because many market transactions are done under conditions. For example, if the price is less than $100, for example, the agent makes the sale. So this is a stopping time. The instant of trading depends also of the information of the market. So after that, we will consider the limits of these portfolios. To do so, we have to choose a closure for L0. Before looking for this good topology, we'll extend some results from discrete time to elementary portfolios. So we'll extend the result to elementary portfolios from discrete ones, and then we will construct continuous time ones. So here we will define a tool that we will use a lot in our work. It's called Conditional Essential Supermem. It was introduced by Baron, Cardillige, and Johnson in 2003. So what is a conditional essential supermem? So we have two sigma algebras, H and F, such that H is a sub-algebra of F, and we take an F measurable function. The conditional supermem given F, or given H of F, will be the minimum, the smallest G greater than F and H measurable. It's the smallest function H measurable greater than F. Analogously, we can define the conditional essential infimum given by the biggest function H measurable less or equal than F. So this tool, we will use it a lot. Now we need a quick definition of what we will call prices for zero. So here we denote by PT big T the set of all prices for zero. Mathematically, it's the set of functions f small t measurable at which we can add some portfolio process and b greater than zero. That is, a price for zero is the initial capital at time t the agent starts with to earn money at the end. So we obtain this set. Naturally, it's important to see what's the minimal capital one can begin with and earn money at the end. So this is why we always see the infimum of this set. Okay, we can characterize this set in the following way. Now, we will define our condition that we call AIP. First of all, I define an immediate profit. What is an immediate profit? It's the possibility to earn money at time big T from a negative price. In other words, we begin with a negative price at time small t and earn money at time big T. We begin with a debt and end up with a positive portfolio value. So, in the contrary, we say that there is absence of immediate profit, what we denote AIP. So it's impossible to begin with a negative price and have a positive portfolio value. Mathematically, we can characterize this by saying that the intersection of the set of prices and the set of prices introduced here. So first capital to begin with and earn money, and the set of negative functions will be equal to 0. Naturally, NA condition implies AIP condition. Now we will give many characterization of our condition AIP. The first one is to say that AIP is equivalent to the infimum of prices for 0 is equal to 0. Now we remark that the set of prices for 0 is a positive code. So if there exists one negative price, the infimum will be minus infinity. This lemma is a very important characterization of AIP. This is the one we work the most. AIP is equivalent to the fact that infimum given FT of all portfolio process is negative. Here, we give another characterization of AIP. It's a link between this condition and the process of prices. AIP is equivalent to the fact that for any T1 smaller than T2, the price at time T1 is greater than the infimum given FT1 of ST2 and less or equal than the supremum given FT1 of ST2. Actually, this theorem has been done by Karadzic and Lipinet, but in discrete time model. Here, we generalized it to elementary portfolios. Then here it's and this theorem we work with the first example of elementary portfolios, that is when the agent trade at arbitrary deterministic times. Here we generalize the equivalence to the case D greater than 1. So we have AIP holds if and only if ST1 is the convex hull of the supremum, the conditional support given FT1 of ST2. What is the conditional support? It's the smallest FT1 measurable closed set containing ST2. So this is the characterization when D is greater than 1. Now we want to give the same theorem, but when the portfolios are indexed by stopping times. To do so, we needed a tool called Maxingales. So what the notion of Maxingales is the analogous of Martingales, but with with the operator essential supremum. So an adapted process is called a Maxengal if the supremum given fs of mt is equal to ms for s small or smaller than t. Here we can also define supermaxengals and submaxengals. And then we establish this result, which is the famous stopping theorem, but with the operator essential supremum. So when we have two stopping times and a maxengal, the essential supremum given fs of m2 will be equal to ms. And the same holds for supermaxengals or submaxengals, and we put the good inequality. So once we have done this result, we were able to prove the same equivalence but indexed by stopping times. Now we aim to construct our continuous time portfolios. So we want to choose the good topology, and our criteria was the following. We wanted to find a topology in such a way that if the sequence of elementary portfolio satisfies IIP, it will be the same for limits portfolio. So if the sequence of elementary portfolios satisfies essential infimum given ft of vtt is negative, this is the characterization, it will be the same for continuous time 1. Unfortunately, it wasn't possible with the convergence improbability, so a conditional closure will be suitably chosen. We will propose two topologies. The first one is defined by what we will call pseudo distance. A pseudo distance is a mapping from L0 to L0, verifying only the triangle inequality. So we define dt plus between x and y by the expectation of the essential supremum given ft of x minus 1 plus infimum 1. This will be a pseudo distance. It's not a real distance, but we can define a topology and a way of converging by this in the following way. So we define balls of radium epsilon centered in some x0 by all the x, such that the pseudo distance between x0 and x is smaller than epsilon. Then we can define neighborhoods by these balls. And then we define open sets by neighborhoods. And finally, we denote dt plus the topology, which is the collection of all these open sets. We can give, we studied really this topology in details, but I will not say everything. I will give some remarks. For example, this topology is not Hausdorff in general. Naturally, we can define a limit, a converging sequence. So a sequence xn will converge to some x if the pseudo distance between x and xn converges to 0. We can also characterize closed sets by the limits of sequences. An important thing to mention is that this as the distance generating the convergence and probability is the expectation of absolute value x minus 1 infimum 1. So we can say that a sequence of elements converges to x with respect to our topology if and only if the essential supremum given ft of x minus xn plus converges to 0 in probability. And almost surely for a subsequence. Here we give other properties of our topology. The sum of two sequences converges to the sum of limit. Here, multiplying a sequence by a function, a positive function, f small t measurable conserves the limit, but we precise that the alpha t have to be positive. Even negative, so if xn converges, minus xn doesn't converge necessarily. Here I give a trivial example to say that we don't have uniqueness of limit. If you consider the constant sequence equal to c, for example, not only the sequence converges to c, but also to anything which is smaller than c. This is why we speak about the set of limits. This is a criteria of conversion. Okay. Here it's a second example of topology that we proposed. So here, as I already said, we want something that conserves the negativity of essential supremum. So this is why we use a lot this tool in our topology. So here we introduce a new distance that generates a conditional convergence in probability. So dt of between x and y will be given by the expectation of essential supremum of absolute value x minus y infimum 1. This tool will be a real distance on L0. We can compare it with the first distance. It's greater than the first distance that we proposed. It's greater than the condition, the distance of converging in probability. So this is why we can say that the convergence for our new topology implies the convergence for the first proposition and the convergence in probability. Also, we can say a sequence of elements converges to x with respect to this second topology if and only if this time essential supremum given ft of absolute value of x minus xn converges to 0 in probability. Here we can give also some properties of this topology. The most important thing is that for this new topology, the function that we multiply with doesn't need to be positive. Okay, if xn converges, minus xn also converges here. L0 will be complete for this new topology, like for the convergence in probability. So here, finally, we can define what we call a continuous time portfolio process by our topology. So a continuous time portfolio process will be, for us, a limit of a sequence of elementary portfolio ones by one of the two topologies. So we have the choice. Okay, we denote by VTT, over line VTT, the set of the continuous time process. So they will be limits of elementary portfolios by one of the topologies. And we reached our objective. AAP holds for continuous time portfolios if and only if AAP holds for elementary portfolios. And this is what we wanted. So all theorems done for elementary portfolios are available in continuous time. We don't have to do the proofs for continuous times. These are some references cited in the talk. And finally, thank you for your attention.
Thank you very much for this nice presentation. Are there any questions from the audience? just unmute yourself and ask right away. All right, seems there are no questions. Everyone is happy. So thanks again for this very nice presentation.
I have a question, so sorry.
Oh, okay, all right. Go on.
So sorry. So I have a question. So I follow this talk carefully, and I see that the suitable topology is not Hausdorff. So how can we deal with a non-Hausdorff topology, and what kind of result did we expect on non-Hausdorff topology?
It's not evident to deal with non-Hausdorff topology. You said that the only good topology is not Hausdorff, but actually it's not the same. But because we have two topologies here, one is Hausdorff and the other is no. But we can deal with it. We can define a topology, and we could obtain results. I think perhaps I didn't understood very much what we want to say.
No, what I mean that if this result makes sense in the financial area.
Yeah, there is actually a good, I will say, interpretation of this conversion way. The continuous time portfolios obtained by this topology will be, we can see them as attainable claims up to some epsilon. So it has really a good financial interpretation. Perhaps mathematically, it's not beautiful to work with non-Hausdorff topology, but financially it has a good interpretation. This is why we have chosen this example of conversion.
Okay, thank you.
You're welcome.
Are there more questions?
Yes, may I ask a question?
Yeah.
If I understand well, if these two topologies lead to saying to two different decisions, because I'm not an expert, but if we take this model, we want to make some decision in financial case. So
yes,
if these two topologies lead to different decision, what can we'll do?
As I already said, one of the topologies implies the other. So actually, I didn't really think about this, but
maybe I can answer.
okay.
Actually, the non-arbitrage conditions are mainly formulated for pricing purposes. That is, first to compute a price that allows you to start a portfolio ending up with some terminal value, and this terminal value corresponds to the payoff of some contracts like European call, European puts, etc. So the first idea is to price. Indeed, the problem of corresponding strategy. So we are talking about decisions. This is mainly what is strategy corresponding to the price time. This is the natural sequence of the work which is proposed to you by Dorsaf here. And actually, indeed, depending on the strategy, the topology you choose, a priori, you're gonna have some different classes of continuous time portfolio process. And this is a good question. This is the same problem for the usual setting in the literature, in the LP case, that the setting, then time portfolio should be a limit in some L2 sense of discrete time portfolio process. And this way of doing actually is convenient for mathematical purposes, but it's difficult to explain from a financial viewpoint. I mean, this is very natural because, for instance, you use for the Brownian motion, Black-Scholes model, etc. So this is very useful. But from the financial viewpoint, of course, as you emphasize, there is no such there's no single approach actually. And what Dorsaf explained to you is finally, for the moment, we are able to obtain a rather large class of continuous time portfolio process, mainly through the topology defined by the pseudo distance, which is financially very, very, to say, meaning. Maybe Dorsaf could write it down, or maybe I can do it if I share my screen, I don't know. Is that actually any continuous time portfolio process may be wished in the sense that from a limit of discrete time process, you can get a value which is larger than. And it's very important to be larger than, because when we say that we may reach a wealth, that is, you have at the end a terminal greater than. So what is important for us is to play with this greater than condition rather than approximately equal in the, for instance, to sense in the setting of the Ito calculus. I hope that my answer is better, but of course, after this is not a problem of decision whether a choice of model. In finance, there are a lot of models, and then at some point you have to choose a model, either stochastic calculus, either maybe one day a model. This is a rather subjective choice depending of course, after in practice, you have to compare and to choose what is the models you think the best one for your purpose.
I don't know if you see my screen, or it's not the case. You see my screen?
We still see the slides.
Okay, this is for Amin and what we got here. This is the financial interpretation of the portfolio obtained by the first topology, which is not Hausdorff. So this is the continuous time portfolio. So it's possible financially to finally attain this portfolio continue up to an arbitrarily small error. So it has a good financial interpretation.
I think we don't see what you're pointing at. I still see the PDF from your slides.
Wait, yes. This is a remark. You're seeing a remark?
No, I don't see it, at least.
I should change. Sorry.
Maybe it's me. I don't know.
No. I have to change what I'm sharing. I don't know if I know how to do it. Sorry.
But yes. Also, we need to go on with the next talk. So
okay, this one. This is
yes.
financial interpretation. So this is the continuous time portfolio, and it's it will be financially unattainable wealth up to a small error. Thank you.